Okay, good morning everyone. So today we will continue for the fundamental part, especially that's a pretty important physics to further understand the semiconductor physics device. So today we will introduce quantum mechanics. So the quantum mechanics basically is if you have followed the undergraduate courses, they might be already the course called the modern physics, or even if you are from the physics department, probably you have followed the course like whole semester is lecture for the quantum mechanics or quantum series here. So to be honest, that's very complicated. It's if you want to learn, you definitely can learn the whole semester or even the several years. And many researchers, they spend their whole life to understand the quantum mechanics here. But in our case, we are only take the most important part. Since this part is already enough for us to understand the semiconductor physics, so we won't lecture the whole bunch of a series. So we will just spend like maybe 1 or 2 classes just to let you know that what will be the most important series, like help us to understand the semiconductor transport, especially related to the carrier transport here. So as usual, I try to bring the final, like the outcome that what we actually expect the quantum mechanics can help us. So I use first to use a typical MOSFET as an example. So I believe right now everyone at this room should already familiar with MOSFET structure, this device. So we have the source, drain, and we have the dielectric, and on top of dielectric we have the gate. And previously we have been already briefly introduced the basic operation and basic characteristic for the MOSFET. So in general is we have the source, which will be N plus region, drain is also the N plus region, and in here we assume the case is a p-type substrate, p-type substrate here, and the normal operation is we will ground the source part, and we start to apply the small bias, for example 1 volt at the drain side. At the meantime, we apply the positive gate bias here. Since we start to apply the positive gate bias, so we can imagine that there's a certain electron can be attractive. So that's due to the basic physics that once you apply the positive gate bias, it certainly the electron can be attracted here. And because this is a perfect insulator, so normally the electron can only stay at this region. So this is our electron. And since we apply the positive drain bias in the right hand side, so we can expect this electron can be flow from the right to the left, right? So that's a pretty like the normal operation. So that's an electron current, and that means our drain current is flow in this way. So that's the typical case for how the carrier transport in the typical MOSFET structure. And based on with this understanding, if you try to plot the most important, the ID VG curve. So now we can expect, first of all, there should be no current because our gate bias is not larger enough. And once the gate bias is larger enough, then you start to have the current flow. So this gate bias need to larger enough to start have the electron inverted and accumulated in the channel. So that's how we usually define this as a threshold voltage here. So that's a typical case that IDVG that we already mentioned in the previous classes. But what do I didn't mention before is that actually there's other possibility to have the current. One possibility is actually in reality, if you try to look up not only the drain current versus gate voltage, but now if we look up the gate current versus gate current, gate voltage. So where is this is gate voltage, and where is the gate current? So that means they could have the current in this place, and that's what we call the gate current. And ideally, since this is perfect insulator, so we should not have any current can be sensed from here, because this is insulator. So what does insulator mean? Insulator means that this should be the material not be able to conducting any carriers. So whatever electron forming here there's no chance to be able to flow in this way. This should be not possible. This should be not possible because that's how the perfect insulator, the function of the perfect insulator should have the capability that blocking these electrons. But in reality, if you try to measure the gate current versus the gate voltage, you will still be able to have the characteristic like in this way. So that means you will find out that there is a gate current you can be sensed from here. And as long as your gate bias increase, and actually your gate current is increased. And this is something that we need to use quantum mechanics to understand, because this characteristic cannot be understood by using the conventional like the Newton physics. So if you look at the classical physics, so we all learn about the classical physics from the high school. The classical physics tell us right now if you have the certain wall, if you have a wall here and you try to throw a ball toward this wall, and there's only one chance, there's only one scenario can be happen, which you will see the ball will rebound. So that means the ball will be reflected, rebound from the wall. So that's a general things you happen in our daily life here. And therefore you won't have a chance to see the balls on the other side of the wall here. So that's a classical physics tells us. But the problem is that if we try to use classical physics to understand our semiconductor, then based on the understanding from classical physics, there should be no current. The gate current should be zero. So that's exactly the case. You have the ball through against certain wall, like the blocking certain, like the wall here. And then the only things can be happen is the ball will rebound and you won't find the ball on the other side. So this is same thing like here. If you imagine this is a ball, you try to throw against this wall. And based on the classical physics, all these electrons can only be reflect. There's no chance that the electron can be observed in here and in the end creating a leakage current. So actually the truth is not like that. The truth is that we can have the leakage current here. That means the classical physics cannot help us to understand the semiconductor device. That's why we have to introduce quantum mechanics here. So the idea for quantum mechanics is very simple. Still the same. We have the wall here, but in here we don't call this as a wall. We just call this as like the barrier. But it's the same meaning like the wall. But right now, if you are not throw the ball, you are trying to throw the carrier, so it can be electron or hole. So right now, if you have the carrier, which can be electron and hole, trying to go through the wall, this barrier. And the first scenario you will still observe is that there is a certain reflection of the carrier. But on the other hand, we also found out that there is a chance you will find out the carrier on the other side. And this carrier become the gate leakage current if we try to increase the gate voltage. So this is quantum mechanics. So the basic idea for quantum mechanics is just trying to tell us that there is a phenomenon, that's how we call the tunneling. So the tunneling, that means that under the certain condition, even you have the insulator here, you have the wall here. Once you throw the ball against this wall, and you will also have the chance to find your ball, which will be observed in the other side, which will be here. So that's why we need to understand the quantum mechanics. That's already the conclusion. And the rest of in the class just mainly like how the equation to prove this phenomenon, and then what other scenarios that we need to understand. But the basic idea is that we have used quantum mechanics to understand why there is a carrier, there's a probability to find the carrier on the other side, which is not possible to be understood from the classical physics. And what this implication for the device characteristic, just like here. Because we can find the carrier on the other side due to the tunneling. That means electron here is possible to tunnel toward the gate, in the end become the leakage current. And finally, we have the some physics that allow us to understand this characteristic. So that's a general idea that why we have to understand the quantum mechanics. If you look at for every like a semiconductor physics book from the beginning is always starting from quantum mechanics. I hope this illustration can make you feel like the quantum mechanics is not that difficult as you saw. Of course, if you follow like a pure physics class, like starting from the pretty fundamental equation, in the end try to illustrate this concept, and most of the students will give up almost like during the half of this journey because of the loss equation is pretty like complicated. It's difficult to understand the point that how this equation want to illustrate. But I hope that with this slide, even the rest of the slide you cannot follow up, but at least the beginning is very important. This just trying to help us to understand why there's a current can be happen even there's a barrier. The barrier can be dielectric or the barrier can be potential barrier, and the rest of we will discuss later. Okay, so that's a brief introduction. Then for sure we start to move further that why these things can be happen in the semiconductor world, not in the general like our living life here. So first of all, why do we need the quantum physics? This is because we want to describe the electrons movement in a micro world. So that means these things only happen. Quantum mechanics, quantum physics can be only applied in the case that's in the extremely small, like the micron or even nanometer. So that's exactly in the scale like our semiconductor device. So if the certain object is large enough, like for example here, and then the typical like a Newton mechanics work very well. So that's why that in the real living world, basically we can use Newton mechanics, classical physics to explain everything very well. But the problem is that if you consider in the micro world, and that's a complete different scenario here. So our original problem is like here, we have the piece of the semiconductor material. And then we are curious like how the electrons transport, moving in this semiconductor material. So that's the original problem. The original problem is just try to understand how these electrons can be moving in a piece of the semiconductor material. But if you look up in more detail, the question become that one that we have to consider the lattice arrangement. So in that case, if we take into account the periodic structure for the lattice, so you will find out that this is semiconductor material is a piece of a material with this lattice arrangement. So in this material, you have the lots of the small atoms placed in the certain arrangement, like here. And then our problems become, we are curious how these electrons movement, but this movement will interact with other atoms here. So that means our problems become like here. The electrons move in the right hand side. Original problem in the large scale, you will see in this way. But if you try to look at in the small scale, actually what the question we are dealing with is electrons moving from the right to the left, but each time will interact with the original atoms in the lattice. So once the electron move here, certainly you will be influenced by this one. Once you move here, you will be influenced by this one. And therefore, actually, the questions become in another sense that this is a question that electron moving in the periodic potential. because I think everyone in this room has a basic physics. Whatever you learn from high school, undergraduate, is like you will know that when certain two objects close to each other, they must have a certain potential happen. And if you try to separate these two things, there's another potential happen. So the question becomes, once it comes here, the potential can be in the one case. And once it moves here, the potential change, then potential back to the certain case. So therefore, we can also start to simplify. The questions become, there is a potential, periodic potential. And now the question is become, we want to understand how this electron movement in the place with the periodic potential. So electron can be here, or electron can be inside here, or back to here. So that's exactly the question that we want to solve here. So just let me try to illustrate again. In the beginning, the question is very straightforward. We are curious how these electrons moving inside the semiconductor material. But you try to look closer for this semiconductor material. The material was made by this periodic structure, and therefore the questions become the electron movement inside this periodic potential structure, and that will be interacting with these atoms. And because it's become like sometimes nearby this atom, sometimes far away from this atom, and therefore the questions become again is electron moving in a periodic potential. So we are curious at what are the electrons' behavior in this place, in this place, or in this place. So that's why we need the quantum physics. So I hope later on, when you see this potential, if you look at for all of the semiconductor booths, it's starting always from here. But right now, I hope you can understand that the implication from this graph is actually considered the case of here, and which is come from this scenario. Okay, so for sure, the next part is we start to get involving with the more fundamental theories and more mathematical calculation. And there's some principle, basic principle, that allow us to further address the question come from the quantum physics here. So the first one is the principle of the energy quantum. So this is the idea, like in the end, of course, we will explain later, but basically you will find out that the energy level is not continuous, it's discrete, so you can quantize the energy level. And then the second part is the wave-particle duality principle. So that means that the carrier can be work as a wave or can be also considered as a particle. And then the third, which is the uncertainty principle. The uncertainty principle. So that's the basic three principles that we will have to use to understand the quantum mechanics. And there's something more. It's pretty like the knowledge from the modern physics. For example, the photoelectric effects. So this is a phenomenon that demonstrates inconsistency between experimental result and classical theory of the light here. So, based on the classical physics, if the intensity of light is large enough, the work function of the material will be overcome and electron will be emitted from the surface, independent of the incident frequency. So that's based on the classical physics. But actually, the observed effect is that at a constant incident intensity, the maximum kinetic energy of the photon electron varies linearly with frequency. So that means if you try to plot here, the x-axis is frequency, and then the y-axis is maximum kinetic energy. And we actually will find out that you insert the light here and you will create some photon electron kinetic energy, which has a frequency dependency. And with limited frequency V equal to V0 here. So that means below this limitation, there's no photoelectron is produced. So that's a quick overview, like what we learned from the modern physics. And the next concept, which is energy quantum. So this comes from the Planck. He assumed, he made this assumption in 90s, that thermal radiation is emitted from the heated surface in a discrete packet of the energy called the quantum. The energy of this quanta is given by E equal to h mu, hv, where v is the frequency of radiation and h is known as a Planck constant. I think that should be something you also learn from the modern physics or the general physics in the undergraduate. So in 1905, Einstein interpreted the photoelectric results by suggesting that energy in the light wave is also contained in the discrete packets or bundles. The party-like packet of energy is called a photon. Whose energy also given by E is equal to hv here. So therefore, the photoelectric effect explains how the discrete nature of photons and demonstrate the party-like behavior of a photon. And the maximum kinetic energy of photon electrons can be considered in here. And where the phi is the minimum energy or work function or is required to remove electron from the surface. So basically, these are the old knowledge we learned from the modern physics. When I was a high school student, I also start to get to know modern physics, or even for the undergraduate. I think for the modern physics, sometimes it's very difficult to immediately to catch the meaning. But the good thing is in the end, always the calculation or the equation is very simple, just like here. So equation is also very simple. But if you're still confused, you should go back to check some fundamental physics, which that can explain this in the further detail. In here, we just quickly go through because this is not the point we will focus on in this class. And next is also, I think that's pretty well known. That's what we call the wave-particle duality. So that means the photon acts both as a wave and particle. The photon can have the wave and particle. And how about the case of the electron here? So there's called the Compton effect. That's a particle-like behavior of electromagnetic. So in 1924, the boy assumed that the existing of the matter wave. He suggests that since a wave exhibits particle-like behavior, particles should be expected to show wave-like property. So the hypothesis of the boy was the existence of the wave-particle duality. So therefore, the momentum of photon can be calculated by this way. By considering this the boy's hypothesis, then we can also use this to calculate the wavelength, the lambda here. So that's a main conclusion in here. So as I say, like the modern physics sometimes very difficult to understand in the first sense, but in the end, the calculation is very simple, like just showing here. Actually, the conclusion is that we can also use this one to calculate the wavelength of the particle. And the next one, I think everyone should be also heard about this already. It's called the uncertain principle here. The Heisenberg uncertainty principle given in 1927 applied primarily to the very small particle and states that we cannot describe with absolute accuracy the behavior of these subatomic particles. So the uncertain principle describes fundamental relation between the variables, including the position, momentum, and also the energy and time here. So there's some formulas showing here. So this is just to illustrate that the momentum P and then the X, there's uncertainty about this. And the energy and then the time, there's also the uncertainty about this. This also in the end will become one of the key conclusion that when we try to understand the electron behavior, we cannot precisely to determine the position, but what we can only know is a probability. Okay, so with all this fundamental knowledge, finally we can start to move on the case that we are interested in to understand the electron movement here. The first case, as I say, we are actually interested in the electrons moving in the periodic structure, which is exactly consider the electron movement in the case with a periodic potential as shown here. And actually with this graph, there's three cases we have to understand. The first one is this one. The electrons might actually moving in the free space. So that's the first one. And second one can be the electrons movement in the potential well. This is a potential well here. Or the electrons in the position that's actually not inside the potential well, but is slightly higher as shown in here. And that's actually give us a different result here. So the first one, that's back to the basic case of the electrons in the free space here. So in this case, and we have the potential in here. We have potential in here. But now we can assume our potential is approached to the zero. So in this case, this is our electrons moves in the free space. So that's the first case. And in the second case, which is the infinite potential well here. So that's in the case here. So in this case, actually, we are consider this is x equal to 0 in the certain distance s equal to a, and the potential is look like here. So we are actually trying to consider the electrons movements inside this potential well. But the other two regions, so we have the region 1, region 2, region 3. This is approach to the infinity. This is approach to the infinity. So that's exactly the case as illustrated here, the infinite potential well. So in the second case, we want to understand that how actually the electrons behavior inside this potential well. And then the third one, which is consider the step potential function. So in this case, it's like we have the region 1 here. We have a region 2 here. So now there's a step potential V here, and we are curious if there's electrons want to move toward this step potential function, and what happened for this the scenario here. So this will be exactly the same one like in this case. And of course, there's still one more. That's even more complicated. That's a case to combine the previous case, but that's more close to the reality. Is that we are consider but right now there's potential barriers in here. So again, there's a 3 region. Region 1, region 2, and region 3. And our electrons will try to move toward the right hand side, but the energy is smaller than this potential barrier here. So this is a false condition that we are interested in. And why this condition is getting more practical in this case, in our case, in a semiconductor case, because this is exactly the case like our MOSFET. As we have already mentioned, with the MOSFET, and once we apply the gate bias here, we all know there's a possibility to have the electrons inverted here. And then actually this electron will be injected from the bottom to top. That's exactly the case like here. So this is our carrier, this is our carrier, and then this electron will face a potential barrier. It's not an infinite potential barrier, it's a potential barrier with a certain fixed height here. And afterwards, the region 3 is again another free space. So this is the case exactly in the end, try to help us to understand what happened here. So we can imagine this is our dielectric. and we try to have electrons in the channel inject into dielectric, and we are curious that how the electrons in the end, the behaviors inside the region 3, because the region 3 is related to the leakage current that we can sense from the gate metal side. Okay, so to further understand each case that we start need to have use some mathematical tools here. The mathematical tools we have to use is Schrödinger's equation. That's very well known, but it's also sometimes it looks like it's scary. But just try to remember that this equation not actually try to confuse you. It's try to prove our physics understanding in the end to indicate that what would be the physics result in the different case here. So we will use this one-dimensional Schrödinger's wave equations, where the equation is shown in here, and where this phi xt, this is a wave function, and Vx is a potential function here. So that's a general, like the one-dimensional wave equation here. And right now we assume that the wave equation can be written in the form of this one. So where phi s is a function of position x only, and phi t is a function of time only. I think that's something you learn from the undergraduate. There's the course called engineering mathematics, and there's a method what we call the separation variable method. So this is exactly we use the separation variable method here. And once we put this inside this one, and then you can start to get the result like here, and further become here. And we can consider the phi t, which can be expressed like here, and therefore this one will in the end also become like in this way. So in this case here, you try to put everything inside, then you will have this E. This will become the E here. So second derivative phi x the most important part is that after all this calculation, in the end, the equations become time independent. This is become time independent in this case here. So we are from the original is time and space dependent, and now it's become the only space dependent, but the time is independent. And again, the wave function phi st is to describe the behavior of an electron in crystal. So, as previously shown that the phi xt can be written as this one, and thus will also return exponential minus j e and then this term is in the end become this one. And then if you do the mathematical trees, try to multiply this twice, and this can be also considered in this one here. And in the end, these ones with a star, that means this negative becomes a positive. So this twice multiple in the end will become as shown me here, because this and this can be cancelled. So now this term becomes like this one. And what does actually this tell us? This tells us that this one is a probability density function and is independent of the time. So that means right now the wave equation in the original is dependent on our space and dependent on time with a certain consideration. Now the probability function is only depend on our space and is independent of our time here. So that means if right now we consider the case we are interested in, which is electrons move to the right, and then the electron in the right hand side is related to the probability and that's only the location dependent only. So that's actually how this equation trying to tell us. So again, that of course, if you just look at the purely all these the equation calculation and all this mathematics, it's sometimes easy to get confused that what does this want to tell us. But try to always to combine the case that we are interested in. So that this is a case in our semiconductor world. We are interested in, again, the electron trying to move toward the right. And therefore, based on this equation, that actually tells that you can only find how do you determine the electrons in here. You cannot determine precisely. You can only consider its probability. And this probability is location dependent only. It's independent of the time. So this is how this equation tries to tell us. Okay, so then let's move for the short summary for this calculation from the wave equation here. So basically, we try to consider all these three basic principle, like the principle of the quantum, the wave particle duality, and also the particle follows the following of the laws of the conservation of the energy here. And therefore, we actually get this equation out. And based on this equation, finally we get this conclusion as shown here. So this conclusion tells us that the wave function is a probability density function, is independent of the time. But now, again, we still have to remind what actually the wave equation is. So, again, the wave equation is to describe the behavior of an electron in the crystal. And now, we also found out that the wave equation is a probability function. So that means to describe electrons in the crystal is related to the probability, as shown, explained by here, and is independent of the time. So that starts to lead into the major difference between the quantum mechanics and then the classical physics. So one major difference between the classical and quantum mechanics is that in classical mechanics, the position of particle or body can be determined precisely. I think that's no doubt. In the general, like a Newton physics, we can easily, precisely to determine everything. So we can determine the position precisely. But in the case of the quantum mechanics here, the position of the particle is found in terms of probability. So again, don't be confused by this equation. So I think the conclusion, physics understanding conclusion is quite very simple. First, what does wave equation mean? The wave equation is generally try to describe the behavior of an electron in the crystal. And after the lots of calculation, then we can find out that wave equation actually is a probability density function, and it's independent of time. It's only dependent on the space, on the location here. So that's leading to the major difference between the classical physics and the quantum mechanics, because in the case of classical physics, everything is precisely determined. But in the case of quantum mechanics, we cannot determine the position precisely. What we can only know is probability, in terms of probability. Okay, so that's the conclusion for the wave equation. And that's also leading to the same one that how do we determine the electron in here is also, we can only understand that how high the electron can be shown. So that's only related to the probability. So it can be only 1%, it can be only 10%, or it can be only 0.1%. This is something that we only know about. Okay, so let's get something more about how the further derive for the equation. You remember that so far we haven't moved on the previous 4 cases. The previous 4 cases is exactly the case that we want to understand, but we are still in the fundamental part to understand the application of the wave equation. So again, this represents the probability density function, and that means if you do the integration from minus to positive, that will be equal to 1. That's for sure, that you integrate every possibility, for sure in the end becomes 100%. So that's equal to 1. And there's some boundary condition. The wave equation and the first derivative must have the following property if the total energy and potential are finite everywhere, which is so that's like the sum of the boundary, because this, you know that in the later on, most of the engineering mathematics, we need to put some boundary condition allow us to solve for the further answers here. So that's a certain boundary condition. So the potential function is finite everywhere. So therefore, the wave function as well as its first derivative is continuous. The potential function is infinite for the case and here, and therefore the wave function is continuous at the boundary, but the first derivative is discontinuous. Okay, finally, we have enough tools allow us to start to understand the case one by one. We just put what we actually all know in the previous slide, and then just put the sum of the condition here. The first one is consider the electron in the free space. So that means the E and Vx is constant. So this one showing here, this is because this is free space, so Ux is equal to 0, and actually that's the Us here means the V here. So that means then the previous very complicated equation can be simplified. So now this become as a 0, and we have this equation. And based on this equation, and from your learning from previous engineering mathematics, so we can know the possible solution for this function. It looks like in this way. This is a general solution for this function. And since this is time dependent, and therefore we can also rewrite the phi t equal to this one, and therefore the phi x, the wave equation, consider the space and time, can be considered as a space wave equation of the space times the t here, and that will be equal to phi x exponential minus j omega t, and where this is equal to here. And also based on this, the solution, general solution, is shown me here. And this solution has a certain physics meaning. The first term with a coefficient, like for example A, is a wave traveling in the positive x direction. And B is a wave traveling in the negative x minus x direction here. But now you can find out that this solution is exactly has the same illusion like here, because we already know the answer, right? If we don't understand all this mathematics, you can already imagine that in the case with a free space, of course, your electron can be moved in the positive x direction, and also the electron can be moved in the negative x direction. So right now, if you forget all of this, with this schematic, of course, in the beginning, we already guessed the right answer. So that's pretty straightforward. You have the electron moving in the free space. That's for sure that only two possibilities can be happen. Moving in the x positive x, or moving in the negative x. But right now, we have the more like the solid proof from the mathematics, because the mathematics also prove that our guess is right. So as I say again, that don't be confused by the wave equation, because it's true that the calculation is very complicated. We have to involve the certain assumption, lots of the fundamental physics and very complicated engineering mathematics. But in the end, just try to remember that the conclusion is very simple, because this is exactly fit what we guess already. And where the k is a wave number can be shown by here. This is because we have wave particle duality. So that's the first case. And the second one, we are curious about the electrons' behaviors in the infinite potential well. So now the particle is assumed existed in region 2. So the particle is contained with in this place. And then in region 2, of course, we always starting from this equation. But in region 2, our Vx is equal to 0. So then Vx equal to 0. Then this equation becomes this way. And then the particular form of the solution is by consider this one here. And of course, with a certain boundary condition that phi x equal to 0 should be phi at the place x equal to a should be also equal to 0 here. Then we can start to solve this one, and then phi x will become like this way. And this is exactly the same one that we learned from the past. This is what we call as a standing wave. So this is an equation for the standing wave. So that means if you have infinite potential well, actually this will have the standing wave like inside this region. So further, we consider this the calculation, and further we try to calculate the wave number, and in the end we found out that on the energy level right now is quantized, is discrete. What does mean the quantized? Quantized means that you can count the energy level separately one by one. That's how we call the quantized. So for example, we have the E1 that's equal to this one. We have the E2 that's equal to this one. So that means our energy right now is become discrete, become separate number that can become one by one. You have a energy E1, you have E2, you have E3. It's not a continuous energy anymore. So that's the concept of the quantization of the energy. So that means the energy of the particle is quantized. That is, the energy of the particle can only have the particular discrete values here. So right now the energy is not continuous anymore. It can be actually discrete by the number 1 by 1. That's how we call the quantization. Okay, so maybe we'll take a 10 minutes break and we'll come back later to further to understand the rest of the case.有我录影。
会放在上面。
哦，放在那个，因为加入那个 FB 啊。
哦，好像。
你要加入 FB 才会看到。
加。
对对对，那你看一下，第一堂课应该有介绍才有。
哦，那个 QR code。
对。
那我先讲。
这边。哦，好。
谢谢老师。
好。第几页？这个吗？
老师写那个还是时间？
哦 ，OK， 应该要对，应该要这个 file， 对，这个 file， 你说是要这个 file 吗？对 ，OK， 好，谢谢。
就是喜欢就是从会觉得比较经验的累积。
对，所以就后来这个也是因为刚好那时候有疫情开始要线上上课，对，所以就被逼的学习一些新东西。然后所以现在上课还OK 啊，对，这应该对你来说都 OK。这个你要少接触的，就是它比较理论的部分，因为你是比较偏实作，对，但是只是说刚好有些理论来，然后跟你实作可以再互相的搭配一下，对，
都要多学习了。
对。那你现在这里修这门课还有那个谁的课？那个忘记你跟我讲，
还有那个郭教授，还是礼拜五的。
但是什么？
光电那个。
都上。
都是听一些演讲，
那也不错，
所以还好。
那也不错啊，那就是多听听。
他今天下午是那个化学系的课。
OK。
那个孙建富。
那你现在这个公司的这样子忙活，这个不用上。
可以啊，
因为你这样上班的在很多。对。因为刚刚我在职博班，他们不是一学期。是啊，
我想说快一点。
对，马上上完，然后就可以开始出现。
对啊。
be absent in the lab meeting tomorrow because I have the machine test in that time. Thank you. For sure.
Okay, so now we'll consider for the next case that have the state potential function. So in here, we consider a flux of particles incident on the potential barrier. So that's the case that we there's incident particles toward the potential barrier here. And so in here we have two regions. One is region 1 and another is region 2. So the wave equation in region 1 is shown me here. Because in the case of region 1, the Vx is equal to 0. And therefore, this equation becomes like this way. And the general solution for this equation is shown me here. So this actually has two implications here. The one with A1, e exponential jk1x. That means this is a traveling wave. In the positive x direction. So that's an incident wave. And then the B1 exponential minus jk1x, that's a traveling wave in the minus x direction. So from this result, I think it's also very straightforward. That can be understood because if we have the incidence of a particle toward the right, and then in the region 1, there could be only the two cases. One is you have the traveling wave in the positive x direction. Another one is you can have the traveling wave in the next negative x direction, minus x direction. So that's even without this equation, that already can have the good guess. But I think right now we have also have the mathematics proof for this case. And in the region 2, the potential is V equal to V0. So now we are wondering the case like here, V equal to V0 here. So again, the equation we have here, and now we assume energy is smaller than V0. So that means our incident, the energy of this particle is smaller than V0 here. And this equation will become like here. And also, the general solution of this equation can be shown in this way. Then the wave function must remain finite. So that means the coefficient B2 is equal to 0. So this one is equal to 0. And therefore, the only possible solution is shown me here, with the x larger than 0. And therefore, with these two equations. One is in the region 1, and this one is region 2. And also with a boundary condition that the x equal to 0 must be continuous, and potential function is everywhere finite. So the first derivative of wave function must also be continuous, and therefore we can have this b1 and b2. This coefficient can be come out with consider the boundary condition like in this one. So in here, actually, the result is if we have the flux of the incident particle, and actually in this case we have the reflective particles. I think that's because we have an incident here. Then for sure that since there is a state potential barrier, so that means it's definitely there's a certain part will reflection. And the reflection coefficient can be found from here. So in region 1, the result of R equal to 1 implies that all the particle incident on the potential barrier for E smaller than V0 are eventually refracted. So that means whatever you injected, it's all reflective, and that is consistent with classical physics. So finally, that's we use the understanding from the modern physics by considering wave equation with some of the potential barrier. In the end, if we consider the case that you have the state potential, but actually all of the particle will be reflected, and that's exactly the same one like the classical physics, that how the classical physics can tell us. So now we found out that this is also the one good way to find out that the classical physics can be also proved by using the modern physics. But if we consider for this special case, and there's some more understanding here is region 2. So for the case when our energy, the energy of the incident particle is smaller than the V0, the coefficient A is actually not 0. So if A2 is not 0, that means the probability density function of the particle can be found in region 2. That means there's a probability here that can find the particle because the A2 is not the 0. So this result implies that there is a finite probability that incident particle will penetrate the potential barrier and exist in region 2. So that means in the region 1, you have a certain incident and certain reflection. But also in region 2, we found that there's a certain particle that can possibly existed in the region 2 as well. As I saying here, the incident particle will penetrate the potential barrier and exist in the region 2. So the probability of particle penetrating the potential barrier is another difference between the classical and quantum mechanics. So as I say, the classical physics definitely cannot predict that there's a particle exist in this region, but the quantum mechanics tell us that there's a chance that the particle can exist in the region 2 here. So what does this imply? So if we back to the case we are interested in, which is MOSFET structure. We have a source, we have a drain. We have a dielectric. And we have a VG here. So that means once apply the gate bias, the electron can have a certain probability exist in the dielectric. So this is something that if we don't have a quantum mechanics, that's definitely is something that we cannot understand. But right now, we believe that even that's the dielectric, but the electron can have a certain probability exist inside this dielectric, inside this insulator. Okay, so the next one is getting more close to the realities. We consider the potential barrier, but now we also consider the tunneling. So, we want to solve the Schrödinger time-independent wave equation in terms of the 3 regions. In each of 3 regions. So now, as I already illustrated that this is the case, we have the barrier only in region 2. So we try to solve the wave equation in region 1, region 2, and region 3 here. And the solution is shown here in the region 1, region 2, region 3. That's a phi x here. And there's the term, what we call the transmission coefficient, that's shown here. So since the potential V is equal to 0 in both region 1 and region 3, so the incident and transmitted velocity are equal. So that means if we have the particle here, incident in this, and there's a chance that they will be tunneling to reach to the other side. So, for the spatial case, when our energy is much smaller than V0 here, then the transmission coefficient can be expressed in this one, and this means there's a finite probability . There's a finite probability that a particle impinging on a potential barrier will penetrate the barrier and will appear in the region 3. So that's a point here. So that's something that we already make a good guess before, but finally we also can have the equation proof that actually indeed that there is a chance for this transmission, and this particle in the end can penetrate and to the other side. And if we are trying to consider for three-dimensional, so there's something just related to, we try to consider the case from one-dimensional to three-dimensional, because in reality the atoms is exhibited in the three-dimensional worlds here. So this just more, but the general concept is the same. We just try to consider the wave series to the atom. In this case, we have to consider the sphere coordinate here. And also, now, if we consider the previous one, that we also apply this separation of variable technique, but now you have to consider the three different coordinates here. In here, we won't go the detail again, because the general concept for the equation derived is the same, but in here just want to consider that now the quantum number is shown in here. So each set of quantum number corresponding to the quantum state that electron might occupy, and therefore again your electron energy right now is quantized and it's not a continuous, it's actually in the discrete values here. So the initial, this is the same. This is something just additional, more related to when we try to extend our case to the three-dimensional that considered for the atoms, and therefore the initial portion of periodic table elements might be determined by using the result of the one electron atoms plus two additional concepts, which is one is a spin and another one is a Pauli exclusion principle, and therefore in the end leading to the four quantum numbers that will be shown in here. Okay, so let's wrap up for this chapter. So the chapter is trying to illustrate the basic for the quantum mechanics and to show that why we need the quantum mechanics, and then how the quantum mechanics is different from the classical physics. And although we already made a good guess in the beginning, but in the end also the equation help us to prove that our guess is correct. So the basic concept for the quantum mechanics is to describe the behavior of electron under various potential functions here. And by using the Schrödinger's wave equation, forms the basis of describing, predicting the behavior of electrons, and most importantly is this is a probability density function. So that means that we cannot precise the electron behavior position very precisely. What we can know is only about the probability. And a result applying the Schrödinger's wave equation to the certain particle is that the energy of this particle is quantized. So that means that's why the energy level is not a continuous anymore. It's in the discrete energy number here. And as a result, applying the wave equation to an electron incident on the potential barrier is that there's a finite probability of the tunneling. So that's in the end, this is the conclusion here. So in the end, if you try to reformulate what we understand in the MOSFET to the more actually the practical drawing that help us to understand the electron tunneling, actually we will prefer to redraw this schematic. We all know this is a MOSFET structure. So this is a MOSFET structure here. So we have the source and drain here. Finally, we can understand that once we apply the positive gate bias here, we have the electron formation in the channel, and because of the dielectric, it works as a potential barrier. So that means the electron actually have the chance to tunneling through the gate metal. In the end, that will become the gate leakage current. So that's a final full picture that what we should know from this the chapter. But in reality, usually we won't analyze the physics lies here. Actually, we prefer to use a concept what we call the Venn diagram. So the Venn diagram, which is you have EC, EV here, and in the beginning, in the previous, we already mentioned that different material has a different band gap, and that's we have the conduction band and valence band, and this is a case of the silicon. So we have the band gap like here. But actually, the dielectric has a large band gap, like in this way. So this is our dielectric. So right now, we can actually use this Venn diagram to illustrate that how the tunneling can be happen. Again, once we apply the positive gate bias here, we will talk about why that the positive gate bias actually in the Venn diagram is pulling down, because that's related to the Poisson equation. But anyhow, we will talk about later. So once you have the positive gate bias, you will start with your knowledge in here. So you can start to expect there's an electron formation in the channel, and where is the electron? This is the region where you have electron here. And because right now you have the tunneling here, so that means the electron will be able to attract it from the right to the left. Tunneling. So that's leading to the leakage current here. So this drawing here is reformed from this device structure, but this drawing is exactly same like this one, right? Just reverse way. It's the same. This is dielectric. This is your silicon substrate. You apply bias here, then you have electron tunneling. So this drawing is exactly similar to the case 4. So since this Venn diagram is very similar to the analysis related to the potential energy voltage difference, so in later on actually people get more prefer to use the band diagram to analyze everything, rather than use this pure like the schematic drawing. This is pure like schematic drawing, but there's not that correlated with the potential. But this one is getting much correlated to the potential energy. And this one is also very consistent drawing like while we do the analysis for the wave equation. So that's why that in the rest of the chapter, and then also in the more professional analysis, we actually prefer to use a band diagram to understand many things. Okay, so since we have already started to move to a little more about the band diagram, and then we start to move for the next chapter, that's something is indeed that we start to talk about how actually the concept of this band coming from, that why we have to consider there's the concept in the band or band diagram and how the electron is moving inside this band. So this is additional, a little more about the quantum theory, but now we're trying to limit in the quantum theory in the case of the solid. Solid is just a solid state that's related to semiconductor. Okay, so again, first we have to introduce the knowledge related to allow and the forbidden energy bands here. So the wave function of the electrons, two atoms overlap, which means that these two electrons will start to interact. So this is a wave function for the one electron. But in reality, you have to consider there are many atoms placed nearby. So therefore, if you consider this is two atoms here, there's a chance that this electron and wave equation will start to interact here. This interaction or perturbation results in the discrete quantized energy level. So this actually resolve discrete quantized energy levels splitting into two discrete energy levels, as shown in here. And this is because if you look at the next slide, now if we somehow start with a regular periodic arrangement of the hydrogen type atoms that are initially very far away, but now we begin to push the atoms together, the initial quantized energy level will split into the band. Split into a band of the discrete energy level, and the effects shown schematically below. So you can see there's start to formation of band if we trying to push the atoms together. So each atom now contains more than one electron here, and suppose the atom in this crystal contains electron up to the n equal to 3 energy level, and therefore you will see the energy versus the distance can be shown in this way. Then, therefore, right now, if we only consider the n equal to 3 level of the valence electron here, the first 2 energy shells are completely full and tightly bound to the nucleus. And therefore, as you know, for the chemistry, we have some ideas really like the 3p that's related to the chemistry to describe how electrons fill in the band. So we also borrow the same concept like here. So the 3p states corresponding to the n equals to 3 and L equal 1, and that contains 6 quantum states per atoms here. And also we have a 3a state corresponding to n equal to 3 and L equal to 0. That contains 2 quantum states per atom here. That's probably still very vague for you, but you have to think about this. If you don't understand, just go back to check the textbook. For the first one, for sure, if you are first time to hear about this, it's always get confusing. But if you try to think about this and look at some more material, it's still be able to digest. So the thing is that the 3s and 3p will start to interact and overlap. At the equilibrium distance, the bond have again split, but now we have the 4 quantum state per atoms. Four quantum states per atoms are in the lower band. And 4 quantum states per atoms are in the upper band. So you can see from this one. So you have this is foreign state here, and this is foreign state in the bottom here. You have original 3p and 3s here, and you try to push them close and close, and that will be split again like in this way here. And right now what we can, this is so original, you have the 2n electron and 2n electron, so that's the total 4n electrons here. But once you push together, that will be split and redistributed of this electron. And electron will be preferred stay in the lower energy level. So now the 4n electron will be here. And the upper one is there's no electron here. And that's start give the idea that if we can define this one as a EC, we can define this one as a EV here. Then the difference between this and this, that's a band gap, energy gap here. And that's why, to simplify, because every time if we have to draw in this way, that's a way too complicated. In here we just propose a way to convey this concept in the simple drawing. So therefore, we start to redraw this in this sense. EC and EV, and the difference between the EC and EV, that's a energy gap, that's a band gap, and this is how we call this as a band diagram. So now you can also, this is very, very important, because in the end, in the later on, basically that the band diagram concept still need to be used all over the time to time. Even in the very advanced research, we still, many understanding still relies on the concept of the band diagram here. So also from this one, because this graph is reform from this one, but also we can understand the bottom one is one full of electrons, so that's why we call the valence band. So basically, this is a place full of electron, and the conduction band is there's no electron. So this is a place no electron here. So if you look at the fundamental understanding of the EC and EV, that also states that below valence band, that's a place full of electron. Above the conduction band, this is a place there's no electron. Okay, so finally, if you don't really follow the previous from the old terms and put together, split to the band and these things, it's fine. What you need to only know about is this one. EC, EV, and this is band gap, EG. And on top of the EC is a place we call the conduction band. Below the EV is a place we call the valence band. And in between this region is usually we call the forbidden energy band. It's place we call the forbidden energy band. And the forbidden energy band from the wording forbidden, it means that ideally there's no electrons exist in this region. That's why we call it forbidden. So that means this is a region that forbidden to have anything. And therefore, as already say, this graph is mainly transformed from here, and then the bottom one is 4n electron. So that means the bottom is a place full of electron. So this is a full of electrons. And the top one is empty. Okay, so that's the things you should know. You should not only know, you should somehow also memorize, because that's way too important. So at absolute 0 degrees, electrons are in the lowest energy state, so they all stay in the lower band. This is place we call the valence band. Will be full and all stay in the upper band. That's what we call the conduction band. Will be empty. The band gap energy between the top of the valence band and the bottom of conduction band is the width of a forbidden energy band. Okay, so that's all the key information you should know for the related to the band gap and band diagram here. And next one is just something like the case that if we consider a one-dimensional periodic potential function used to a single crystal lattice. So as you previously in our discussion with the wave equation, you probably already consider like we have already considered the case like here, or we consider the case like in this way. So that's the case we are consider. But in reality, you actually have many like the lattice, the atoms in the crystal. So you actually have the many periodic potential function like in this way. So you have a many potential function, and that can be do something to do this calculation here. So as we previous from the quantum mechanics problem, the more interesting solution occurs for the case when energy level is smaller than this potential barrier, which corresponding to the particle being bound with crystal. The electrons are contained in the potential well, but we have the possibility of tunneling between wells here. So the Cronin-Penny model is an ideal periodic potential representing a one-dimensional single crystal, but the result will illustrate many of important features of quantum behavior of the electron in the periodic lattice. So this just for your information that there's a case called what we call the Cronin-Penny model. That's considered that one-dimensional periodic potential as shown here. Basically, it's just an expansion of what we have already derived before. What we already discussed is the case like here, or the case like here. But now this just expanding to the full periodic potential. And there's also another concept, that's how we call the K-space diagram here. So showing here, this is energy, and this is related to the P, that's related to the momentum here. So basically we have this equation, the constant of motion parameter K is related to the practical momentum for the free electrons. And once we do the certain calculation, we can have this one. In the end, it's become like in this case, 1 over n star is equal to 1 over h, the second derivative of the energy versus K here. So especially these n stars mean this is effective mass. So that means this is a certain mass of your carrier. It can be the mass of an electron or mass of a holes here. So the curvature of E versus K diagram near the minima of the conduction energy is related to the effective mass of the electron. So that means because this second derivative, the E versus the K, that's exactly to illustrate the curvature of here, right? If you just try to think about this, you will understand. The second derivative is just calculate the curvature. So the curvature of this one is related to the effective mass of the electron. In this case, we consider the electron. Okay, so the previous related to the Cronin-Penny model, a K-space diagram, that's a little bit additional concept for your information. In the future, you also time to time will find out some people discuss the effective mass, and they will use the K space diagram to illustrate something. And in here, we also still come back trying to understand that how the electrical conductions in solid. Again, in the beginning, it's always use these two-dimensional like the drawing to illustrate that how the electron flow in the lattice. For example, if we have the electron here want to flow in the another side, but that's just pure like a schematic drawing. Actually, we have not that fully understand the physics inside. But actually, this movement from the electrons from here to here can be also understood from the Venn diagram. So we have the EC, EV here, and we have the EG, that's a band gap here. So from previous understanding, we already know that below EV is a place full of the electrons. And when we have the current conduction in the solid, the schematic is showing that you have the electron move here to there. That's create the current. But in terms of Venn diagram, that means you have the electron jump from the valence band across to your forbidden band energy and reach to the conduction band. And remember, this is place that is empty. And this jumping from here to here, that has a current. So in this case, the conduction in the solid right now can be perfectly explained by the Venn diagram. So now you see that why the Venn diagram is important, because it has a multiple function help us to understand many things in the semiconductor. So therefore, that's why if you look at in the beginning, that when we talk about the band gap, then you will find out that the band gap is a material number that actually reflect the different certain material property. So for example, if we have the silicon, that's a EG1 here, and we have the silicon. And as you know right now, the current, if there's a current, that means the electron can jump across the band gap and reach the conduction band. But right now, if we have another material has a larger band gap, again, if the same conduction would like to happen, that means this need to be overcome and reach to the conduction band. And that's become difficult, right? Because as you see from the drawing, your EG2 is already larger than EG1. So that means actually your current in the I2 should be smaller than the I1. Right? So right now, from the Venn diagram, from the drawing, the difference between the EC/EV, that's a band gap. From the drawing of band gap, we can also estimate that how about the possibility to have a current in this material. And as a larger band gap, it's more difficult for the electron to jump from the bottom to the top. So that means your current is smaller compared to the I1 here. If you back to the introduction part, I have drawn the band gap with respect to different material. We have a germanium, we have silicon, we have a silicon carbide, gallium nitride, we have the diamond. And I already mentioned that the diamond has the largest band gap, and that should work as insulating. So ideally, the current, the conduction in the diamond is very difficult. So that not only from the purely like the the common sense, I think everyone in this room should always know about it's difficult to have the conduction of a carrier in the insulating material like a diamond. But right now, these things can be also be explained perfectly illustrated from the Venn diagram. So in the end, you also have to try to make sure that the knowledge that you learn can use a simple concept to use some real life example. Try to make sure that the understanding makes sense, because once that makes sense, probably you won't forget, because that can be easily use a real life example to understand these things. Okay. Okay, so that's this is the energy state in the valence band on complete full and state in the conduction band are empty. That's already mentioned here. This is full and this is empty here. And when the current is larger, when the temperature is larger than 0K, some electrons have gained enough energy to jump to a conduction band and have left empty state in the valence band. So it's illustrated in here. So that's become the current, right? So this is exactly the region. This is drawing this way. This is a region that we are referring to here. So this is a case when temperature larger than 0K, but you know it's never to have the case exactly at 0K. So it's always have under the K, no matter how small K could be, but it's always larger than 0K. As long as you're larger than 0K, the electrons in the bottom always gain some energy, try to be excited and jump up to the conduction band and become the current. And since we have mentioned the K-space diagram, this is something more related to K-space. Is the difference between the direct and indirect band gap. So this graph is related to the direct band gap here. And the direct band gap, it means that if you look at this is electrons here. So the electrons jump from the valence band to the conduction band. That's exactly in the same position of at K. So in this case, K equal to 0. But in the case, what does the indirect band gap is the one like the right hand side. So indirect, that means you have if you want to have the current, first you need to energy, but also you need another momentum. So that's two things. This one is only need one energy, but in these things you need one energy, you need another momentum. So that's become very complicated to have the current. So that's why in most of the case, in direct band gap, like for example, silicon, this is in direct band gap. So you never see people say they can use the silicon to make the light emitting diode. You know what's a light emitting diode? That's a LED. Because LED, it need to have the current transport in the material. And this current transport need to be very efficient. That's why it can emit the light here. But in the case of the indirect band gap, because the efficiency is very low, so that's not possible to have a light emission. But in the case of this one direct band gap, you can have the light emission, and which is very famous one is gallium nitride base LED. So gallium nitride base LED, if you look at this projector, inside the projector lamp, that's a LED. If you look at you buy the the car, no matter for the motorcycle, scooter, or the real car, it's about lighting is always made by the LED. So I believe right now LED is in our daily life. That's a technology pretty accessible for us. But the inside LED is mainly made by the gallium nitride material, and this is because the gallium nitride is a direct band gap. So that's why that we can have a high, very good, the light emission efficiency. So this is something that why we have to understand the K space, because that's related to the direct or indirect band gap material. Okay, and since we have been start talking about the conduction in the solids here, now of course being the engineer, we're not only curious about the band gap, but in the end those things have to transform, becomes a current, because in the end our goal is try to understand the current versus the voltage relationship, no matter what kind of bias you want to apply, gate bias, drain bias, or even just a two-terminal bias. What we always curious about the currents versus voltage, and therefore we have to consider how to have the current equation out here. In the first part, we consider the drift current. So drift current is a current is basically due to the flow of the charges here. So can be considered in these equations here. And if a force is applied, so if we apply the certain force and it start to gain the energy, and if external force is applied to electron in the conduction band, and there are empty energy state in which electron can start to move here. And this is a schematic of the asymmetric distribution of electrons in E versus K diagram, which an external force is applied. Since once there's an external force applied, you can start to expect that there's a current will be able to transport. And before we continue to talk about the current transport, then there's also one thing is important, is that we need to understand what does mean the density of state function. That's usually we call this as a DOS. Since current is due to flow of the charge, so before we calculate the current, important state in the process is to determine the number of the electron hole that will be available for conduction, right? So if you want to have the current conduction, first you have to understand how many electrons and holes that are available for conduction. So the number of carriers that contribute to conduction process is a function of the number of available energy or quantum state. So now you see that before we calculate current, we have to first understand how many carriers are available. But now you can already, from previous knowledge, you already know that if there's they should be have the electron hole, but first we have to determine that the available energy or quantum state that can allow this electron hole to be placed there. So therefore, we have to understand this state here. So therefore, we must determine the density of these allowed energy state. We must determine the density of these allowed energy state as a function of energy in order to calculate electron and hole concentration. So that's why this is called the density of state. So you can imagine that the state is just like the available seats, right? So first we have to estimate how many available seats in this classroom. Because once we have 100 seats, then we can determine there will be the 100 people in this room. And since we have 100 people in this room, that means we have 100 electron hole. And 100 electron holes that can contribute as a current. So that's the logic behind that. Determine the current, first you have to determine how many carriers. But if you want to understand how many carriers, but you need to first understand how many available state that allows this carrier can be sit there. And that's exactly the same idea that how many available seats in the one classroom. Because the total student in this classroom is never exceeded the total available seat in this classroom. So therefore, we have to understand, we have to try to calculate the density of state function. So that's the goal, because the density of state function, in them we can calculate the electron and hole concentration. So regarding for the density state function, that there's something more equation shown me here. So the density of a quantum state is a function of energy, can be shown in here. And as the energy of these free electrons becomes small, the number of available quantum states decrease. And as shown, also this is the same one like this one. And in here, we won't go detail how this equation come out, because that's a pretty like a fundamental equation calculation. In here, we just apply the result in the case that we are interested in. So regarding to a density state can be considered the two parts. One is allow electron energy state. Another one is in the conduction band. Another one is allow electron energy state in the valence band. And it would be more, have some more sense if we plot it. So I think right now everyone should pretty clear that the EC and EV. So that's the top and bottom of the band diagram here, and this is energy here. And by consider the allowed energy state, if we try to plot this equation in this graph, it will look like in this way. And if you try to plot this one in here, it will become like. Of course, right now you're still a little bit confused about what's the purpose to here, but later on you'll be pretty clear, because sometimes you need to a little bit patient to wait until the loss, and finally you will get understanding that why we have to spend the time to describe this in the beginning. So as I say, this is a function of the versus conduction band. This is a function versus a valence band. And also, one thing is related to the semiconductor, not like the classical physics. Sometimes since we cannot determine the things precisely, and there's always a concept related to probability. And to consider to have some good estimation of the things, everything once we have the probability inside. The good thing is we need to use the statistics knowledge, 统计学. So that's why in many domains in semiconductor, it's very often that we have to use statistics. Statistics is not probably we all learn from the high school. I'm not sure that because you guys are not in the same age like mine. So at least in my high school, I learned some basic statistics. But in the university, in the undergraduate, to be honest, unless you are the one who has some interest in the minor major in the, for example, economics or mathematics. Otherwise, I guess most of you might not very familiar with the statistics in the undergraduate classes because that's not necessary for everyone. But in semiconductor, you need a statistics, so it's time to good to pick up something back. But the good thing is that we don't need everything for the statistic. We just need to certain part because remember that we are the engineer. What the engineer do is we try to grab something that benefit for us to address our challenge. We are not the fundamental chemistry, fundamental physics. We have to understand everything. No, we just grab something that's useful for us. So in dealing with the large number of particles, we are interested only in the statistical behavior. Statistical behavior of the group as a whole, rather than the behavior of each individual particle. So that's a key thing. We are interested in the whole bunch of group behavior, and therefore that's why we need to have the statistic. We're not interested in the individual one. And consider the statistic and the probability function. While I was a student, of course, right now I have been in the field for many years. But if we're back to my first class related to semiconductor, I think the concept related to probability function, density of state, probability density function, that's very confused if you are first time to get in touch with this knowledge. But it's just anyhow it's just related to that there's a things that related to we cannot determine precisely. So that's why I always come up with the concept with probability. But I hope in the future that you will more get used to this term. So in there's several probability functions that can be take care to address in the different domain. The first one is the Maxwell-Boltzmann probability function, which can be written in this way that we have Fe that's equal to exponential minus E minus EF over KT here. So this is the particle considered to be distinguished by being number with no limit of number particle allowed in the energy state. So that's in the case of the gas molecule. So that what does it mean? That will not limit in the particle of allowed in each energy state. Because like in this classroom, you can imagine that if you consider you want to put in as many as a gas inside this room, there's always no problem because there's no seat issues, right? So that's how this means. No limit number of particles allowed in each energy state. So this can be only applied in the case of the gas molecules. A second part, which is much more important for us, is what we call the Fermi-Dirac probability function. And this is equation is showing like here. 1 plus exponential here E minus EF over KT. So the particles are again indistinguishable, but now only one particle is permitted in each quantum state. So this looks like it's exactly the case that we are working on. So that's to many describe the electron in the crystal. Of course, there's a third one called the Bosch-Einstein function, and this is the equation. Just quickly go through. Exponential E over KT minus 1. So the particles are indistinguishable, and there's no limit number of particles per mean in quantum state. So that's related to case of the photon. Sorry. Okay, so we will start the class today. So I think we have been already lectured many things, but the idea is, I believe right now you get a sense of quantum mechanics. Right now you understand that we are dealing with things that there's uncertainty, and also because this uncertainty probability, so we have to start to use some statistical tools to help us, and we will move on to talk more in next week. Okay, so we will stop here and see you guys next week.